March 23, 1945. Remagen, Germany. The metal pontoons made a hollow clang beneath Captain James Morton's boots as he strode across the partially assembled bridge. Dawn was breaking over the Rhine River, Germany's last great natural barrier, as engineers worked frantically in the pre-morning light. Artillery fire erupted from the eastern bank, sending fountains of water skyward where shells missed their mark. The distinctive whistle crack of incoming rounds punctuated the constant rumble of war. "Keep moving! We need this section secure in 15 minutes!" Morton shouted over the cacophony, his voice barely audible above the sounds of combat and rushing water. The 30-ton sections of the mobile assault bridge, nicknamed MAD by the men who assembled it, were being maneuvered into place by exhausted combat engineers. Each prefabricated section measured exactly 16 feet wide by 24 feet long, designed to interlock with adjacent pieces with a precision that seemed impossible under combat conditions. Across the river, German 80 mm guns fired from concealed positions. Their muzzle flashes briefly illuminated the hillsides before shells screamed toward the American positions. A round struck 50 yards upstream, sending a column of water and debris skyward. Men instinctively ducked, then immediately resumed their work. "Sir," a lieutenant approached Morton, his uniform soaked from river water and sweat. "3rd Battalion reports heavy resistance on the east bank. They're pinned down and requesting immediate support." Morton glanced at the incomplete bridge, then at his watch. "Tell them 30 minutes. Not a second sooner." His gaze drifted to the eastern shore where American infantry huddled in hastily dug foxholes, taking fire from German positions. 2 miles behind the front, General Dwight D. Eisenhower watched the operation through binoculars from an observation post on a hillside. Beside him stood General Omar Bradley and a small cluster of senior officers. The Supreme Allied commander lowered his binoculars and turned to his staff. "If we can't get armor across that river within the next 6 hours, we'll lose our momentum," Eisenhower said. His face betrayed no emotion, but the gravity in his voice was unmistakable. "How soon until the bridge is operational?" "Engineers estimate 2 hours to complete the main span, sir," Bradley responded, "but German artillery has excellent coverage of the crossing points." "We've already lost 2 sections to direct hits." Eisenhower nodded slowly. "And yet we have no alternative. Berlin is 300 miles beyond that river, and every day we delay gives the Germans time to regroup." He raised the binoculars again, focusing on the strange-looking bridge sections being maneuvered into place. This bridge design, being assembled under devastating fire, represented the culmination of 3 years of secret work by a man who had never intended to become a military engineer, a captured British officer who had turned imprisonment into innovation. On the bridge, Morton felt the structure shudder as another section locked into place. The MAD bridge's unique design allowed each segment to be transported on a single truck, then rapidly deployed and connected without specialized equipment. Its load capacity of 70 tons meant it could support even the heaviest Allied tanks. Most crucially, its modular nature allowed damaged sections to be quickly replaced without compromising the entire structure. An artillery shell screamed overhead, landing in the water just 10 yards from the eastern edge of the bridge. The shock wave rippled through the metal structure, but the bridge held. The design had proven remarkably resistant to nearby explosions, another feature that distinguished it from conventional military bridges. "5 more sections to go!" shouted the engineering sergeant beside Morton. "We're ahead of schedule, sir." Morton nodded grimly, knowing that German observers would be calling in increasingly accurate fire as daylight strengthened. The race against time was measured in minutes and yards, each section bringing them 16 feet closer to the opposite shore where American troops waited for the armor support that would break the German defenses. Back at the observation post, an aide approached Eisenhower with a folder marked "Top Secret." Inside was a single sheet containing the technical specifications of the MAD bridge, a design that had traveled an extraordinary journey from conception to deployment. "Remarkable," Eisenhower murmured as he studied the document. "And to think this design was created by a prisoner of war using stolen pencils and scraps of paper." The mad bridge had not existed in any form 3 years earlier. Its creator, Major Alan Menzies, of the British Royal Engineers, had been captured in 1942 during the fall of Singapore. What should have been the end of his contribution to the war effort had instead become the beginning of his most significant work. On the bridge, Morton felt the vibration of the final section locking into place. Engineers swarmed over the connection points, securing bolts and checking stability. A Sherman tank waited at the western approach, engine idling, prepared to be the first vehicle to test the completed span. "Bridge secure, sir," reported the engineering sergeant, his face streaked with sweat and grime. "Ready for traffic." Morton raised his hand, then dropped it in a sharp gesture. The Sherman's engine roared as it began to move forward onto the bridge that should never have existed. A bridge conceived in captivity, designed in secrecy, and now deployed under fire. The fate of the Allied advance into Germany, perhaps the outcome of the war itself, now rested on the shoulders of a man who had conceived his revolutionary design while sitting in a German POW camp 3 years earlier. July 23, 1907, Aberdeen, Scotland. The granite walls of Marischal College gleamed silver-grey against the morning sky as young Alan Menzies walked beneath its Gothic spires. Rain had fallen overnight, leaving Aberdeen's signature stone buildings with a polished sheen that locals took as a point of pride. The 17-year-old's footsteps echoed on the cobblestones as he approached the engineering department, application papers clutched tightly in hands calloused from summers working alongside his father, a master stonemason. The son of William and Margaret Menzies had shown exceptional aptitude for mathematics from an early age. In the family's modest home on Hardgate Street, Alan had spent evenings calculating load-bearing capacities of bridges he'd designed with pencil and ruler, impressing his primary school teachers with his precision and spatial reasoning. His father's work on Aberdeen's iconic granite structures had instilled in him an appreciation for how materials and forces interacted. Knowledge that would one day save thousands of lives on a distant battlefield. After graduating with honours from Robert Gordon's College, Menzies secured a coveted place at the University of Edinburgh's engineering programme. The university's stone buildings and ancient courtyards became his home for the next 4 years as he immersed himself in structural engineering principles. His professors noted his particular fascination with bridges, not the massive permanent structures that spanned the Forth, but temporary deployable designs that could be assembled and disassembled rapidly. "Most students dream of building monuments that will stand for centuries," remarked Professor Ian McAllister during Menzies' final review. Young Menzies here seems preoccupied with structures designed to exist for mere weeks. Curious focus, but his calculations are impeccable. Menzies graduated in 1929, his thesis on rapid deployment bridge structures earning special commendation. It explored innovative joint systems that allowed prefabricated sections to connect without complex tools or specialized knowledge, an approach that departed significantly from conventional engineering wisdom of the time. The global economic depression that followed severely limited engineering opportunities. Menzies found work with the Scottish Highway Authority, where his unconventional thinking initially branded him an outsider. Traditional engineers scoffed at his proposals for modular infrastructure components that could be manufactured in factories, then transported and assembled on site. "Bridges have been built the same way for generations, lad," his supervisor had told him after rejecting a particularly innovative design. "Stone and steel, placed by skilled hands. Your factory-made pieces might work on paper, but this is the real world." Despite the skepticism, Menzies persisted. By 1935, he had refined several designs for rapidly deployable temporary bridges intended for emergency infrastructure repair. His approach incorporated lightweight materials and ingenious joint systems that reduced assembly time by 60% compared to traditional methods. A successful demonstration during flood relief efforts in Perth brought his work to wider attention. When Germany invaded Poland in 1939, Menzies, like thousands of other professionals, volunteered for military service. His engineering background and specialized knowledge of portable bridging made him particularly valuable to the Royal Engineers. Commissioned as a lieutenant, he underwent abbreviated military training before joining the British Expeditionary Force deployed to France. The winter of 1939–40 found Menzies stationed near the Belgian border with the 9th Field Company, Royal Engineers. The period later known as the Phoney War gave him time to study existing military bridging equipment, particularly the folding boat equipment, FBE, and small box girder bridge. He filled notebooks with observations on their limitations. Too heavy, too complex to assemble under fire, too vulnerable to artillery. Menzies' commanding officer, Major William Hartley, recalled their discussions during those months. He wasn't satisfied with anything, said our bridges would collapse under sustained tank traffic, said assembly took too long, said a single shell could render the entire structure unusable. Irritating chap really, but damnably correct on every point. The German blitzkrieg that began on May 10th, 1940 thrust Menzies' theoretical concerns into harsh reality. As panzer divisions sliced through Allied defences, his company received urgent orders to prepare defensive demolitions while simultaneously establishing crossing points for retreating forces. The contradictory demands, destroy bridges while building others, highlighted the critical importance of mobile bridging capability. During the chaotic retreat toward Dunkirk, Menzies' company became separated from the main British force near Arras. Working frantically to establish a crossing over the Canal de la Bassée for retreating infantry, they came under direct attack from advancing German armour. Menzies supervised the completion of a pontoon bridge under artillery fire, remaining behind to ensure all British troops crossed before preparing demolition charges. The explosion successfully dropped the bridge, but Menzies and 17 engineers found themselves stranded on the wrong side. For 6 days, they attempted to move west toward Dunkirk, travelling at night and hiding during daylight hours. On May 29th, just miles from the evacuation beaches, they encountered a German mechanised patrol. In the brief firefight that followed, half the men were killed or wounded. The survivors, including Menzies, were taken prisoner and transported east. As the truck rattled across France toward Germany, Menzies stared through the slats at collapsed bridges and twisted metal that had once been river crossings. His engineer's mind analysed each failure, cataloguing weaknesses, envisioning alternatives. "They've registered every bridge as a target," he murmured to the wounded sergeant beside him. "When we come back, we'll need bridges they can't predict. Bridges we can put anywhere, anytime, in hours, not days." The sergeant managed a pained smile. "When we come back, sir? That's assuming quite a lot." Menzies nodded absently, his mind already sketching designs. "When we come back," he repeated with quiet certainty. What the Germans didn't realise was that by capturing Major Alan Menzies, they had given him something engineers rarely have in wartime: time to think. December 12th, 1941. Auflag 7B, Eichstätt, Germany. The morning bell rang at 6 a.m., echoing through the stone barracks of Auflag 7B. Major Alan Menzies rose from his narrow bunk, his breath visible in the cold air. The prisoners' quarters, a converted monastery perched on a limestone hill above the Bavarian town of Eichstätt, housed over 1,500 Allied officers. Menzies had been here for 8 months, enough time to establish a routine that helped preserve his sanity. "Another glorious day in the Führer's hospitality," remarked Captain Thomas Edwards, a Royal Artillery officer who occupied the adjacent bunk. "What's on your agenda, Menzies? More of your mysterious scribblings?" Menzies nodded as he straightened his threadbare uniform. "The Germans count us twice daily and feed us poorly. Beyond that, my time is my own." This was the strange paradox of officer-prisoner camps. Unlike enlisted men who were forced to work, captured officers were protected by the Geneva Convention from labour requirements. The resulting idle hours became both curse and opportunity. After morning roll call and a breakfast of watery coffee and dark bread, Menzies made his way to what prisoners called the University, a room in the West Wing where captured professors and teachers conducted classes for fellow prisoners. In a corner of this room, he met with what had become known as the Bridge Club, 5 engineers who shared his interest in military bridging problems. "I've been thinking about our river crossing dilemma," Menzies said, spreading out a homemade chessboard that served as cover for their real discussions. As guards passed by, the men appeared to be engaged in a simple chess match. Captain Roger Simmons, formerly of the Canadian Engineers, moved a pawn forward. "What dilemma might that be?" "The one that got us all captured," Menzies replied quietly. "Our Bailey bridges take too long to build under fire. Our floating bridges can't handle heavy tanks. And both types are sitting ducks for German artillery." The men nodded. Military bridging had changed little since World War I, while tanks had grown heavier and artillery more accurate. The Germans had demolished Allied bridges faster than engineers could build them during the 1940 retreat. Menzies had spent months gathering intelligence from new prisoners and the carefully censored German newspapers that reached the camp. From these sources, he built a picture of the war's progress and the challenges Allied forces would face when they eventually returned to mainland Europe. "We'll need to cross dozens of rivers to reach Berlin," he said, sketching on a scrap of paper hidden beneath the chessboard. "Rhine, Weser, Elbe, each one a natural defense line, and the Germans will destroy every bridge as they retreat." Lieutenant James Wilson, the youngest of their group, frowned. "So we need bridges we can build very quickly, under fire, that can carry tanks." "And that can't be knocked out by a single lucky artillery hit," added Menzies. Using stolen pencil stubs and paper scrounged from Red Cross packages, Menzies began designing a new type of bridge. His first sketches showed a modular system where identical sections could be quickly connected. If one section was damaged, it could be replaced without rebuilding the entire bridge. "The key is redundancy and standardization," Menzies explained to his colleagues. "Each section must be strong enough to stand alone, light enough to be moved by hand if needed, and simple enough to be assembled by tired men under fire." The Bridge Club met daily, refining the design through countless chess games. They calculated load capacities using mental arithmetic, lacking slide rules or reference tables. They debated materials, construction techniques, and deployment methods. Major Robert Phillips, who had worked for a steel company before the war, suggested a crucial innovation. What if each section floated on its own? No need for separate pontoons or supports. This breakthrough led to the distinctive hollow box design that would later make the Maybe Bridge immediately recognizable. Each section would be a sealed hollow box, providing buoyancy while containing all necessary connection hardware inside removable waterproof compartments. The camp's hidden network of craftsmen contributed to the project. A former draftsman created proper technical drawings on stolen German stationery. A metallurgist advised on alloy compositions that would balance strength and weight. A former factory foreman developed simplified assembly procedures that required minimal training. Security was paramount. The bridge designs were hidden in plain sight, disguised as chess notations, poetry, or personal letters. When guards conducted searches, papers were hidden in loosened floorboards or wall cavities. "If the Germans realize what we're doing," Menzies warned his colleagues, "they'll separate us all and destroy our work." By early 1943, the basic design was complete. The mobile assault bridge, mockingly codenamed MAD for Menzies' absurd dream by some skeptical prisoners, existed as a complete set of specifications, assembly instructions, and performance calculations. Now Menzies faced a new problem: how to get the designs to Allied hands. Escape attempts from Oflag 7B rarely succeeded. The camp's hilltop location made it easy to spot escapees, and the surrounding Bavarian countryside was hostile territory for English-speaking fugitives. The opportunity came unexpectedly. In September 1943, Menzies and 30 other officers were transferred to a camp in Italy. The Italian armistice with the Allies had just been signed, throwing the prison camp system into chaos. During the rail journey south, Menzies and 4 other prisoners cut through the floor of their cattle car and dropped onto the tracks near the Brenner Pass. For 3 months, the escapees made their way south through the mountains, aided by Italian partisans. The bridge designs, photographically reduced and hidden in the heels of Menzies' boots, travelled with him through countless close calls with German patrols. In December 1943, a ragged, emaciated Major Alan Menzies appeared at British lines near the Italian front. In his possession, the complete plans for what might be the most important bridge design of the war. January 5, 1944. Combined Operations Headquarters, London, England. The windows of the conference room at Combined Operations rattled as a V-1 flying bomb detonated somewhere in the East End. None of the officers seated around the table flinched. Such interruptions had become routine in London. At the head of the table, Brigadier William Stanton tapped his pipe against an ashtray and regarded Major Alan Menzies with undisguised skepticism. "So you expect us to scrap our entire bridging program based on sketches you made in a prison camp?" Stanton's voice carried the weariness of a man who had seen too many miracle weapons promised and too few delivered. Menzies, still gaunt from his ordeal, stood beside a table where his designs were spread out. 3 months of proper food had not erased the physical effects of captivity, but his voice was steady as he replied. "Not scrap, sir. Supplement. The Bailey Bridge serves its purpose admirably for semi-permanent crossings. But we need something faster, more flexible, for assault operations." Colonel James Richardson from the Royal Engineers studied the drawings with narrowed eyes. "These load calculations, they seem optimistic. You're claiming a bridge built from these hollow sections could support a 70-ton Churchill tank?" "The load is distributed across multiple sections, sir," Menzies explained. "Each connection point transfers stress to adjacent units. It's the same principle as an arch bridge, but with standardized components." The room fell silent as the officers examined the plans. Major General Sir Percy Hobart, commander of the 79th Armoured Division and an innovator in specialised armour, was the first to speak in support. "I've lost tanks to collapsed bridges and destroyed crossings," Hobart said. "If this design works, it solves our most critical mobility problem. I say we build a prototype." Stanton sighed, relenting. "Very well. You'll have resources for one prototype section. If it performs as specified, we'll consider further development." What followed was a whirlwind of activity as Menzies' prison camp sketches were transformed into precise engineering plans. The experimental bridging establishment at Christchurch received orders to construct a single prototype section according to the MAB specifications. Engineers who had spent years perfecting the Bailey Bridge system initially regarded the new design with professional jealousy. "Looks like something a schoolboy would draw," remarked Chief Engineer Thomas Wilson as he examined the blueprints. "These hollow flotation chambers will collapse under the first shell fragment." Menzies, assigned as technical advisor to the project, spent 16-hour days refining specifications and overseeing construction. The first prototype section measured exactly 24 feet by 16 feet and weighed 12 tons, heavy, but within the transport capacity of standard army trucks. Its hollow-sealed chambers provided buoyancy, while the upper deck was reinforced with a lattice of steel supports. On March 15, 1944, the prototype was ready for testing at the Christchurch facility. Military observers and engineering staff gathered as the section was lowered into a man-made basin. It floated precisely at its calculated waterline, its deck remaining 18 inches above the water surface. "Now the real test," Menzies said, as a 40-ton Churchill tank rumbled toward the floating platform. The engineers fell silent as the massive vehicle crawled onto the bridge section. The platform dipped slightly, stabilized, then held firm. Applause broke out among the observers. Even the skeptical Wilson nodded in grudging approval. "It holds," he admitted, "but a single section isn't a bridge. Can they be connected under combat conditions?" The next phase of testing answered this question. Teams of engineers practiced connecting multiple sections in various conditions. At night, in simulated artillery fire, in driving rain. The unique locking mechanism Menzies had designed allowed sections to be joined in under 3 minutes by teams of just 8 men. Most critically, damaged sections could be removed and replaced without compromising the entire structure. By May 1944, with D-Day approaching, the MAB design had moved from skepticism to priority production. Factories in Birmingham, Leeds and Glasgow that had been manufacturing Bailey Bridge components were partially converted to produce MAB sections. The first production units rolled off assembly lines as Allied forces stormed the Normandy beaches. Material shortages threatened the program as steel alloys were diverted to other urgent wartime needs. Menzies worked with metallurgists to redesign components using available materials, substituting aluminum for steel in non-critical elements and incorporating high-tensile wire reinforcement where weight reductions were needed. "We're cutting it fine with these material substitutions," Menzies told General Hobart during an inspection tour of the Birmingham factory. "But the bridges will hold." Hobart nodded, watching workers weld flotation chambers. "They'd better. We're planning river assaults all the way to Berlin, and these bridges are now essential to the timetable." Training specialised engineering units to deploy the bridges became the next challenge. The Royal Engineers and US Army engineers established joint training facilities where troops practiced assembly procedures until they could perform them blindfolded. The goal was to reduce deployment time to under 90 minutes for a complete 100-yard span, a fraction of the time required for other bridge types. By December 1944, as Allied forces approached the German frontier, the first MAB bridge units were positioned near forward supply depots. Strategic planners recognized that the Rhine River would represent the final major geographical obstacle before the German heartland. Intelligence reports indicated the Germans were systematically destroying bridges as they retreated eastward. Field Marshal Bernard Montgomery, commanding the 21st Army Group, reviewed the bridging plans with Menzies personally. The meeting took place in a requisitioned schoolhouse near the Belgian border. Maps of the Rhine crossing points spread across classroom desks. "These bridges of yours, Major," Montgomery said, tapping a proposed crossing point near Wesel. "They're now the linchpin of our entire Rhine strategy. Without rapid bridging capability, we lose our momentum just as we reach Germany proper." Menzies traced the twisting blue line of the Rhine on the map. "The bridges will work, sir, but they'll need proper artillery support during deployment. The sections are resilient, but not invulnerable." In January 1945, the first full MAB bridges were deployed across the Rhine River during Operation Blackcock. The successful crossings validated the design under actual combat conditions, though German artillery fire destroyed several sections during assembly. The modular design proved its worth as damaged sections were quickly replaced without abandoning the entire crossing. As Allied forces pushed toward the German border in early 1945, convoys of trucks carried disassembled MAB components forward. Menzies' prison camp sketches transformed into hundreds of tons of specialized steel, ready for the moment that would determine their worth. March 22, 1945. Allied Forward Headquarters, Linnich, Germany. The map room buzzed with activity as officers marked troop positions along the western bank of the Rhine. Red pencil lines indicated known German defensive positions. Blue arrows showed planned assault routes. Major Alan Menzies studied the terrain models of the crossing points, his finger tracing the contours where the MAB bridges would soon be deployed. "Water levels are higher than anticipated," he noted to Colonel Richard Barnes, commander of the 998th Engineer Treadway Bridge Company. "The current at Remagen is running at 8 knots. That will put additional lateral stress on the bridge sections." Barnes nodded, making notations in his field book. "We've compensated with additional anchor points. First and fifth sections will have double cable moorings upstream." Operation Plunder, the massive Allied crossing of the Rhine, represented the culmination of years of planning. The Rhine was not merely a river, but a symbol, the historic boundary of German territory. A psychological barrier whose crossing would signal the inevitable defeat of the Third Reich. Every detail of the crossing had been meticulously planned, from the massive artillery preparation to the airborne drops of Operation Varsity that would secure the eastern bank. Major General William Hogue approached the table, his expression grave. Latest intelligence confirms what we suspected. The Germans have destroyed every standing bridge across the lower and middle Rhine. They've positioned their remaining 88mm guns to cover all logical crossing points. Menzies was not surprised. The Germans understood the strategic significance of the Rhine as well as anyone. Their defense would be fanatical. That's why we're not using logical crossing points, Menzies replied. The MAB bridges can be deployed at locations they won't expect, away from pre-registered artillery targets. Throughout the night, engineer units moved into position along a 30-mile stretch of the Rhine's western bank. Trucks carrying disassembled bridge components followed blacked-out routes to staging areas, guided by military police with shielded flashlights. The Germans, anticipating the crossing attempt, fired periodic artillery barrages across the river, the shells exploding in predetermined patterns designed to disrupt preparations. At 2 a.m. on March 23rd, the Allied artillery response began. Over 3,000 guns opened fire simultaneously, their muzzle flashes turning night into artificial day. The thunderous barrage focused on German observation posts, artillery positions, and suspected defensive strongpoints. Under this covering fire, the first engineer teams began moving their bridge sections toward the water's edge. Menzies, serving as technical advisor, moved between crossing points in a mud-spattered jeep. At the Wessel crossing, he found engineers struggling with a modified connection system installed on the latest bridge sections. "The locking pins won't seat properly," shouted Sergeant Michael Collins over the artillery noise. "Tolerances are off by at least a quarter inch." Menzies dropped to his knees in the mud, examining the connection point by flashlight. The problem became immediately apparent. The newer sections had been manufactured with slightly different specifications due to material shortages. The aluminum alloy replacement parts had expanded differently under field conditions. "Hand me that adjustable wrench," Menzies called. Working quickly, he modified the connection brackets, opening the tolerance just enough to accommodate the variation. "Try it now," he instructed the engineers. The sections joined with a satisfying metallic clank. Collins looked at Menzies with newfound respect. "Good thing you were here, sir." "Good thing I designed the bloody thing," Menzies replied with a tight smile. "Carry on." As dawn broke over the Rhine, the first completed MAB bridges extended partway across the water. German artillery fire intensified as improved visibility allowed their observers to direct fire more accurately. A shell impacted directly on a bridge section near Ries, tearing a 10-foot hole in the decking and killing 2 engineers instantly. "Clear the damaged section," Menzies ordered, watching as the troops implemented the contingency they had practiced dozens of times. The damaged section was disconnected, pushed aside, and a replacement floated into position, all while under direct fire. 15 minutes later, the bridge was operational again. At the Xanten crossing, a different problem emerged. The current had shifted a partially assembled bridge nearly 30 yards downstream, threatening to break it apart. Menzies commandeered 2 assault boats, directing their crews to secure additional mooring lines to the drifting structure. For 20 minutes, they fought the current, gradually pulling the bridge sections back into alignment. By mid-morning, the first Allied tanks began crossing the completed bridges. The distinctive rumble of Sherman tracks on metal decking echoed across the water. German artillery continued to target the crossings, but with diminishing accuracy as Allied counter-battery fire systematically eliminated their guns. Menzies stood at the western approach of the Wesel Bridge, watching a column of tanks move across his creation. Each massive vehicle caused the bridge to flex slightly before returning to position, exactly as designed. The MAB bridges were performing precisely according to specifications, allowing armor to cross at a rate of 1 vehicle every 30 seconds. Field Marshal Montgomery arrived at the Wesel crossing point shortly before noon, his beret tilted at its characteristic angle. He surveyed the bridge with obvious satisfaction, then spotted Menzies standing nearby. There you are, Major, Montgomery called, gesturing for Menzies to join him. Your bridges are performing splendidly. We're moving across faster than anticipated. Menzies nodded respectfully. Thank you, sir. The men did the real work. Montgomery fixed him with a penetrating stare. Don't be modest, Major. This crossing operation would have been delayed weeks without your design. These bridges have saved thousands of lives and will shorten the war considerably. A nearby explosion sent water cascading over them as a German shell landed in the river. Montgomery didn't flinch, merely wiped water from his face and continued watching the tanks roll across the bridge. By nightfall on March 24th, Allied armoured columns were streaming across Menzies bridges, breaking into the German heartland. The last great natural barrier of the war had been overcome. German resistance east of the Rhine, while still fierce in places, was fragmented and disorganised, unable to form a coherent defensive line. In his field notebook, Menzies made technical notes about the bridge's performance, stress patterns, deployment times, damage response. But he also allowed himself a moment of personal reflection, writing, "The bridges worked, design principles sound, primary objective achieved." What he didn't write, but felt deeply, was a sense of completion. The bridge concept, born in captivity, refined through countless prison camp discussions, smuggled to Allied hands at great personal risk, and developed against institutional skepticism, had proven its worth in the crucible of combat. His contribution to victory was tangible, measured in tanks crossing, troops advancing and lives saved. May 9, 1945. Berlin, Germany. The Brandenburg Gate stood scarred but intact against a smoke-filled sky as Soviet and American forces celebrated victory in Europe Day. Thousands of miles of advance, millions of casualties, and 6 years of total war had culminated in Germany's unconditional surrender. Among the countless factors that had contributed to Allied success, the rapid Rhine crossings of March 1945 stood as a pivotal moment. The final breaking of organised German resistance and the opening of the route into central Germany. 2 months after those crossings, Major Alan Menzies sat in a requisitioned office in the Allied Control Commission headquarters, completing his final technical report on the mobile assault bridge performance. The document catalogued deployment statistics, structural integrity assessments, and damage reports from each crossing point. The data confirmed what commanders had already recognized. The MAB bridges had shortened the war by weeks, perhaps months. "Remarkable accomplishment, Major," said General Omar Bradley, who had stopped by the office unannounced. "Your bridges carried over 12,000 vehicles across the Rhine in the first 48 hours. The Germans never recovered from the speed of our advance." Menzies stood to attention, surprised by the general's presence. "Thank you, sir. The engineers who deployed them under fire deserve the real credit." Bradley waved away the modesty. "We're recommending you for the Distinguished Service Order. Winston Churchill specifically mentioned your contribution during the Victory Cabinet meeting." The recognition was gratifying, but Menzies found greater satisfaction in the technical validation of his design principles. The official after-action reports confirmed that despite taking direct artillery hits, no MAB bridge had failed catastrophically. The modular design had proven its worth. Damaged sections were quickly replaced without compromising entire crossings. 3 weeks later, Menzies received orders to return to England. His war was over. As his transport plane circled over the English countryside, he gazed down at the rivers and streams below, automatically assessing them as crossing problems to be solved. The habit would never entirely leave him. Post-war Britain offered new challenges for Menzies' engineering talents. The country's infrastructure had suffered tremendously from German bombing. Roads, railways, and traditional bridges needed reconstruction throughout the country. In 1946, now Colonel Menzies declined an offer to remain in the military and instead joined the Ministry of Works as a senior civil engineer. "Your MAB design principles could be applied to civilian emergency bridging," his new superior explained during their first meeting. "We need rapid solutions for communities cut off by damaged infrastructure." Within 2 years, Menzies had developed a civilian variant of his military bridge. The rapid emergency viaduct system retained the modular approach and quick assembly features of the MAB, but replaced military-grade materials with commercially available components. When flooding in Yorkshire destroyed key bridges in 1948, Menzies' civilian bridges restored transportation links within days rather than months. As reconstruction gave way to new development in the 1950s, Menzies established his own engineering consultancy. The firm specialised in innovative bridging solutions for challenging environments, from remote Scottish Highlands to developing nations with limited infrastructure. His approach consistently emphasised simplicity, modularity, and ease of deployment with minimal specialised equipment. Bridges connect people, Menzies explained to engineering students at Edinburgh University during a 1956 lecture. The most elegant design is worthless if it can't be built where it's needed, when it's needed, with available resources. The MAB design, meanwhile, evolved within military circles. The US Army Corps of Engineers developed the ribbon bridge system, incorporating Menzies' floating modular approach with modern materials and assembly techniques. NATO standardized similar bridging systems across member nations, ensuring compatibility in multinational operations. Military historians gradually recognized the strategic significance of the Rhine crossings and the bridging technology that made them possible. Professor Harold Williams of the Royal Military Academy Sandhurst wrote in 1962, "The rapid Rhine crossings represented a textbook example of how technological innovation can create strategic advantage. Menzies' bridges turned what might have been a protracted final campaign into a rapid advance that hastened Germany's collapse." For decades, however, Menzies' contribution remained largely unknown outside military engineering circles. The classified nature of the original development, combined with Menzies' natural modesty, kept his story from public awareness. While other wartime innovations like the Bailey Bridge were celebrated in engineering textbooks, the MAB remained relatively obscure. This changed in 1972 when declassified documents revealed the full story of the bridge's prison camp origins. The Sunday Times published a feature article titled "The POW Who Built Bridges to Victory," bringing Menzies' achievement to public attention for the first time. At age 65, he found himself suddenly celebrated as one of Britain's unsung war heroes. "I never saw it as heroic," Menzies told the interviewer. "It was a technical problem that needed solving. The real heroes were the men who built those bridges under enemy fire." The renewed interest prompted the Imperial War Museum to request Menzies' original prison camp sketches and notes for permanent exhibition. These artifacts, carefully preserved over decades, now occupy a display case alongside other examples of wartime innovation and ingenuity. In military engineering schools across NATO countries, the principles Menzies developed continue to influence modern combat bridging doctrine. The US Army's M104 Wolverine and the British Army's BR-90 bridge systems, despite their advanced hydraulics and composite materials, still incorporate the fundamental design principles of modularity, rapid deployment, and resilient connections that Menzies conceived in captivity. Alan Menzies passed away peacefully in 1989 at his home in Edinburgh. His obituary in the Times described him as the engineer whose prison camp sketches became the bridges that carried Allied armies to victory. The Royal Engineers erected a memorial plaque at their headquarters in Chatham, recognising his contribution to military engineering. Perhaps the most fitting tribute came from General Dwight D. Eisenhower's memoirs, published years after the war. The rapid Rhine crossings represented the moment when German defeat became inevitable rather than merely probable. The bridges that made those crossings possible were essential to our final victory. Modern composite materials and computer-aided design have transformed military bridging technology, but the core principles remain unchanged. When American forces crossed the Euphrates during the 1991 Gulf War, their ribbon bridges descended directly from Menzies' MAB concept. When NATO forces deployed emergency bridges after Balkan flooding in the early 2000s, they used systems that incorporated his modular approach. What began as desperate sketches on scraps of paper in a prison camp had become the bridges that carried Allied forces to final victory, proving that sometimes the most powerful weapon in war is not a gun or a tank, but the human mind.